All right, this is the CS2316 final project, Nicholas Hoyt and Stephanie Sun.
So our point of interest, purpose, and expectations, we chose to focus on the US EV market and looking at how the incentives, charging infrastructure, and EV demand patterns correlate with each other across states. We chose to choose this topic because it's relevant both today and in the future due to sustainability and environmental concerns.
All right, so for the CSV data collection, we searched for uh, data on electric vehicle consumption in different parts of the United States. And then HTML, we found ours when we were searching for states that had better electric vehicle readiness, such as EV charging ports in different parts. And then for the JSON, we were looking to see different types of EV charging infrastructure in different places. So we found that, and there were inconsistencies found in all three of them that we needed to be cleaned.
So for the CSV, we use pandas in order to access the file, and there were a lot of empty rows and columns. So we used drop NA and the threshold to drop rows and columns that were more than 55% empty. And then this data set also had duplicate column names that referred to different data. So we used a loop to differentiate the first and second occurrence. And then for those differentiated columns, we renamed them based on what the data was pointing to. And we restricted the data to just 1900 to 2100. So those are the years that we were looking at. And we converted blank cells to zero and percentages to floats. And then the previous loop did not capture the column 1990 to 99 due to the dash 99. So we did another for loop for that cleaning. And then we rounded all of the floats to 5 decimal places and then cleaned the text space columns to finally output it as a CSV. Now for the HTML, we used Beautiful Soup to parse through a Wikipedia page and convert the first table that was on EV incentives to a data frame. Then we cleaned the text, renamed the columns, and converted the incentive amounts into clean numeric values. Next, we standardized the vehicle type column by mapping different types to a standardized type, and then converted carpool axis to be Boolean, and then included only necessary columns in a copy to and renamed the column so it would be easier to use in future analysis.
All right, for the JSON, we needed to load the API keys and request the JSON, and then we only kept data that was had columns more than 50% filled, so that we didn't have too many empty values. And then we used a loop to replace any NaN values with NA or zero, depending on if there was an object or not for the data, if the data type was an object or not. And then we use pandas to better format the output data and take care of any inconsistencies with different stir methods. For example, stir.contains is when we wanted to, like, if we wanted to find out is Tesla, we would find out if it contained Tesla to add to our new generated column. And then we created a list of final columns that we wanted to include in the final data frame and returned it. Our insight one, so using our cleaned incentive CSV file, we started by importing the necessary sklearn methods that we needed to use. And then it was erroring on the first try, so I had to do some more cleaning to make all the values to either 0 or 1 so that they could run through the logistic regression model. And then Y is what we were predicting. We're predicting if it had a cache incentive using the data from incentive amount, vehicle type, and carpool axis. And then we pre-processed it so that one hot encoder would help clean the vehicle type, and then with incentive amount, it would be standard scalared so that it would be either a numerical amount. And then we use pipeline to run the logistic regression model, and then we split it up with 80% train, 20% test, so that we could have a accurate model that could predict. And then with this, we concluded that the incentive amount, vehicle type, and carpool lane access can accurately predict if it had EV incentives because we got a 1.0 accuracy, so it's very good. And then using the county data CSV file, we wanted to create a linear regression model to predict future years shared by counties. We use df.select data types to add only add columns that contain only floats or ints, and then we clean up the columns with NaN values to fill them to either 0 or unknown. And then we set the Y variable to 2009 so that we could predict the 2009 fuel share. And then we set our data and then ran it through this preprocessor so that our data would all be clean and ready for the linear regression model. And then we did split it again, and then we achieved an R squared value of 0.966, which proves that the model can explain all the variation from from the predicted 2009 fuel share. And our mean absolute error was basically 0, so it ran perfectly.
So for incentive three, we used the incentives and fuel station. Sorry, insight three. We used the incentives and fuel station CSV to look at how strongly state EV incentive amounts relate to their charging station infrastructure. So first we mapped the state names to abbreviations and then found the mean, median, and number of incentives for each state, as well as the ratio of private stations and Tesla stations. And then we also created an infrastructure score to analyze the quality of charging stations. And we found that incentive size has almost no correlation with total station count and is mildly negatively correlated with Tesla network and private access ratio. For Insight 4, we used county and fuel station CSV to analyze whether the availability of public charging stations in each state is aligned with actual EV demand. And we took the most recent column to find the EV demand by state, and then we normalized them to find an infrastructure gap metric. Then the analysis showed that several states have substantial infrastructure gaps, meaning their EV ownership levels are not matched by sufficient charging availability. Finally, Insight 5, we use the county and incentives CSV to examine whether state level EV growth is meaningfully influenced by EV incentive amounts. So we use the first and last columns of EV demand to find the average rate of change. Then we found the correlation between average incentive amount per state to the average change. And we found that there's a slightly negative correlation, meaning states that offer higher rebates do not necessarily experience stronger EV growth. So financial incentives might matter, but are not the dominant driver of EV adoption.
All right, so visualization one, I created a pie chart to see the most common incentive types used from clean EV incentives. We counted them with value counts and then created them into percentages. Visualization two, used the county data CSV to show gas consumption by state in the year 2000. This was because we wanted to see which states were more likely to have more incentives because the ones that use more gas, they would want to incentivize people to switch to electric cars.
And in visualization three, we use the fuel station CSV to see whether high Tesla network presence also provide publicly accessible charging infrastructure, which shows how equitable the EV system is. And after aggregating the number of stations and distinguishing private and Tesla, we found, and using a line of best fit, we found that high Tesla dominance tend to have lower public access percentages, suggesting Tesla heavy states may rely more on restricted or semi-private charging networks. And the main challenges, results, and conclusions. Our main challenge was accessing the JSON file with the API key, and then accessing and cleaning the CSV, especially in Google Colab. Secondly, for the results, EV incentives showed almost no correlation with EV growth, and states show mismatches between their EV incentives, charging infrastructure, and actual demand for charging. And also, Tesla heavy states tend to have more restricted charging environments. So, from that, we can conclude that no single policy lever is sufficient. Financial incentives are limited in impact, and infrastructure must scale with demand, including charging equity.
All right, these are our data sources, and thank you.